In this section, we are studying antidifferentiation. The last two chapters, we've been looking at derivatives and their interpretation as slope geometrically and as instantaneous rate of change in applications. This section is about doing that backwards. Basically, we're going to be given a function and we might be asked, well, if this is the derivative of some function, what was the original function? How do I get the original function back? To get rid of a derivative, you do what's called taking the antiderivative. We're going to talk about standard notation and terminology for antiderivatives. We're going to go over the basic antidifferentiation rules and how they're related to your derivative rules. And we'll talk about some simple techniques for algebraic manipulation to make an expression that doesn't look like one of our rules look more like one of our rules. So that's the plan. So let's start with the definition of, or the standard notation for an antiderivative. So if I want the antiderivative of a function f with respect to x, it's notated this way. This is called an integral sign. It will have more meaning later. This dx over here tells you the variable you're taking the antiderivative with respect to. So if this says the antiderivative of f with respect to t, this would be a dt. But really, when I'm taking an antiderivative, I'm focused on this function here. And I'm asking myself, what function can I take the derivative of that will give me this function back? This right here is red, the antiderivative of f with respect to x, and I'll abbreviate with respect to as WRT. And then we're going to say that equals some function f of x, capital F of x, plus c, where if I take the derivative of capital F, I get little f back. So that's the definition. And if you're wondering where that plus c comes from, we'll see in just a moment. Okay, so let's look at a derivative and then try to think through what we would have to do to undo that differentiation process. So let's say we started with the derivative of x to the fifth, and I get the antiderivative of x to the fifth, or excuse me, the derivative of x to the fifth comes from using the power rule, right? We bring the power down and multiply by x to the 1 less power. So the derivative of this is this. Well, that's equivalent to saying the antiderivative of this function is x to the fifth plus c. And if you're saying to yourself, how is that equivalent? Well, let's see. If I take the derivative of this x to the fifth plus some arbitrary constant, I should get this function back. That's what this notation means. The derivative of this has to equal this. So let's check. So we say to ourselves, what's the derivative of x to the fifth plus c? I bring my 5 down, I multiply by x to the 1 less power, and then I add the derivative of a constant, but we know the derivative of a constant is 0. So that's 5x to the fourth. So since the derivative of this is this must be the antiderivative of this function. Now I say the antiderivative, but what I really mean is I've got a family of antiderivatives right here. All of these functions that are almost exactly the same have the same slope. They all have the slope given by f prime equals 5x to the fourth at a particular value of x. That's the formula for the slope. So let's look at a different one. Let's say I'm taking the derivative of, let's say x squared. Derivative of x squared is, when I bring the power down, multiply by x to the 1 less power, so that's 2x. So if the derivative of this is this, the antiderivative of this must be this, because we're undoing differentiation. Now again, if I take the derivative of this side, the derivative of x squared is 2x, and the derivative of this c is 0. I'm calling this the antiderivative, but again, it's a family. It's actually infinitely many functions. If I take the derivative of any one of those functions, I get 2x. Let's look at that family. Okay. So that family is given by y equals x squared plus c. When c equals 0, we get something that looks like this. Oops. This doesn't look very much like a parabola, but you get the idea. It's supposed to be a parabola. If c equals -1, we would just start down here. Oops. And my graph would look like this. If c equals 2, the graph looks like this. And it actually really doesn't matter what c is. C could be -5, -1, -2, -3, -4, -5. And if I had drawn my graphs a little bit better, it'd be a little bit more obvious, a little bit easier to see. This is y equals x squared minus 5. The pink graph is y equals x squared minus 1. We've got y equals x squared in black. And the blue graph is y equals x squared plus 2. I hope you see that all of these have the same slope at a particular x value. At x equals 1, they all have a slope of 2. Rise over run is 2 at x equals 1. It doesn't matter which graph I'm on. At x equals 2, the slope of each of these graphs is 4. Since it's exactly the same shape, just shifted up or down so many units, all of these graphs have the same slope. So it actually makes a lot of sense that the antiderivative would have this plus c in it. Because if I take a graph and I move it up and down, it doesn't change the slope of the graph at all. So this antiderivative of 2x, we call it the antiderivative of 2x, but it's actually a family of functions. It's all of those parabolas. All of those parabolas that are shifted up and down some arbitrary number of units. C could be 1,000,000. It could be y equals x squared plus 1,000,000. So it'd start up all the way up here at 1,000,000, and then it would go up. And that'd be totally okay. If I take the derivative of that, I'm still going to get 2x. Okay, so that's the idea behind antiderivatives. Let's go through our basic derivative rules and come up with the appropriate anti-differentiation rules for it. for those rules. It's basically the reverse version of all of the rules we've already learned. First of all, we know that the derivative of a constant is 0. Since that's true, the antiderivative of 0 is just a constant. Because if I take the derivative of the constant, I get 0 back. We know the derivative of a constant times x is just a constant, because that's just a line that passes through the origin. It has a slope of k. So the antiderivative of that constant with respect to x is that constant times x plus c. And again, think about it. If you took the derivative of this, the derivative of a constant times x would just be the constant. The derivative of the c would be 0. So if I take the derivative of this, I get this back. Now what about this? If the derivative of e to the x is e to the x, what's the antiderivative of e to the x? I hope you said e to the x plus c. The derivative of e to the x plus c is just e to the x plus 0. So got that one. About the derivative of x to the n. This one is a little bit more complicated. When I'm thinking about undoing this process, I need to undo whatever I just did in order to compute the derivative. But I have to do that in the reverse order. So whatever I did, I have to undo it, well, like I just said, in the reverse order. We'll see in just a second. Bring the power down is how we take the derivative, and then we multiply by x to the 1 less power. So the last thing I did when I took the derivative of this was I subtracted 1 from the exponent. So to undo that subtracting 1 from the exponent, I'm going to add 1 to the exponent, and then rather than multiplying by an exponent, I'm going to divide by that exponent. Okay, so let's look at a few examples of these. Just simple examples. Oops. The antiderivative of 0 is a constant. There's not really an example I can show you there. I might ask myself, what's the antiderivative of 5? The antiderivative of a constant is a constant times x plus c. So the antiderivative of 5 is 5x plus c. Antiderivative of e to the x is e to the x plus c. Example is exactly like the rule. Not much going on there. Here, let's check this one out. Antiderivative of x to the 4th. Well, using this rule, I have to add 1 to the exponent and then divide by the new exponent. Let's check this one. So I've got x to the 5th over 5, and I want to take the derivative now. Oops, plus c. Well, according to our derivative rules, I would pull out the constant first. So that's a 1/5. And then I multiply by the derivative of x to the 5th. Well, the derivative of x to the 5th is 5 times x to the 1 less power. The derivative of the constant is 0. The 5 and the 1/5 reduce, and I get x to the 4th. Is that what I have over here? It sure is. So this works out. Okay, so we've got our rules. Now there was one thing I forgot to mention. This is more terminology. This whole thing represents the antiderivative of f with respect to x. This is called an integral sign. this dx over here tells me the variable of the variable I'm anti-differentiating with respect to. So we sometimes call that the variable of integration. And this function right here is called the integrand. So this is an antiderivative. And the function f of x plus c, we use capital F for the antiderivative, and then we have the constant of integration over here. This is called the antiderivative of f with respect to x. This is also called an indefinite integral. Those two terms are interchangeable. I don't tend to use the word integral here. I tend to use the word antiderivative because it reminds me that I'm undoing differentiation and I'm finding a function. I'm finding actually a family of functions. Now again, this is called the integrand. And this whole piece right here is called an indefinite integral. We'll talk about what definite integrals are a little bit later. Okay, so when I'm checking this rule, I'm saying the antiderivative of x to the fourth with respect to x, I use my power rule. I add 1 to the exponent, divide by the new exponent, and add c. When I'm checking this rule, I take the derivative of the antiderivative, and I get this. When I'm done, I'm comparing it to this function right here, and that's called the integrand. So the derivative of the antiderivative should be the integrand, this function right here in front of the dx. Okay, so we've got these 4 rules. Now, notice that this rule, we're going to have a problem with this rule if n is equal to -1. Because if n is equal to -1, I'd have an x to the -1 plus 1, that's x to the 0 over 0. And we can't divide by 0, that doesn't make any sense. So this rule works as long as x is not, or as long as n, excuse me, is not -1. If n is not -1, I add 1 to the exponent and I divide by the new exponent. And now you're going to see where this comes from. The derivative of natural log of x is 1 over x. And this is true when x is positive, because remember, we can't take the log of a negative number. Now I want to show you one other thing. If I take the derivative of natural log of -x, if you're saying to yourself, Miss Townsend, you just said I can't take the log of a negative number. You're right, we can't, but this isn't negative. In this case, -x has to be positive. The domain of this function is 0 to infinity. The domain of this function is -infinity to 0, so that what's inside here is positive. So I can take the derivative of this using the chain rule. We get 1 over the inside function, and our inside function is -x. And then we multiply by the derivative of the inside by the chain rule. And we know the derivative of the inside is -1. So I've got -1 over, or 1 over -x times -1. And that's 1 over x. So the derivative of natural log of x is 1 over x, and the derivative of natural log of -x is 1 over x. Now I'm going to put these two pieces together and remember this fact. absolute value of x. It has that V shape if you look at its graph. Absolute value of x is x when x is greater than or equal to 0. And it's negative x when x is negative. It looks like that. On this side, that's the graph of y equals x. On this side, that's the graph of y equals negative x. So it has that slope of -1. So absolute value of x actually takes care of x and negative x at the same time. So I can put these two pieces together and I can come up with a new rule that says the derivative with respect to x of natural log of the absolute value of x is 1 over x. I hope you see that when I take that x and that negative x, and I see that those are just two branches or two parts of this absolute value graph. If the derivative of this is 1 over x and the derivative of this is 1 over x, that must mean, since absolute value of x is this, the derivative of natural log of absolute value of x is this. Of course, we're assuming that x is not equal to 0. So that's a derivative rule. Imagine what the antiderivative rule is. The antiderivative of 1 over x is natural log of the absolute value of x plus c. Because the derivative of natural log of the absolute value of x is 1 over x. Whether x is positive or negative, this is going to give us this. Okay, so I've got that rule. It's not really an example to show because it's a single rule. Now notice also that this 1 over x can be rewritten as x to the -1. So if I see something in my integrand that looks like this, x to the -1, I never use the power rule. Don't add 1 to the exponent and divide by the new exponent. If I see something that's raised to the -1 power, I write it as 1 over the same thing raised to the +1 power. And then I remember, oh yeah, the antiderivative of that is a log. Okay, so we've got these 4 rules. The antiderivative of 0 is a constant. The antiderivative of a constant with respect to x is that constant times x. Antiderivative of e to the x is e to the x. And the antiderivative of x to the n, when n is not -1, is x to the n plus 1 over n plus 1. We add 1 to the exponent and we divide by the new exponent. And the antiderivative of 1 over x is natural log of the absolute value of x. Okay, so we've got 5 rules here. Let's look at some example problems. Oh, actually, let's do a couple more rules, a few more rules first. Now, this actually makes a lot of sense given our rules about derivatives. Remember this rule? If I take the derivative of a constant times a function, well, I can pull that constant out and then just multiply by the derivative of that function. So when I'm undoing that, it makes perfect sense that I would just pull that constant out here as well. The antiderivative of a constant times a function is the constant times the antiderivative of the function. Now, if I'm taking the derivative of a sum of 2 functions, well, the derivative of the sum is the sum of the derivatives. So we get f prime of x plus g prime of x. Well, if I'm undoing that, so I'm going from here to here, it makes perfect sense that the antiderivative of a sum is the sum of the antiderivatives. Because I'm just doing what I did over here, but in reverse. So we've got some rules now. See if we can't add a couple more rules. This one we don't use very often, but it comes up occasionally. The derivative of natural log of a to the x. This is an exponential function with base a. A is just a number, it's just a constant raised to the x. Is exactly the same exponential times natural log of the base. So let's look at a concrete example. The derivative with respect to x of 5 to the x is exactly the same exponential times natural log of 5. So the slope of this graph is exactly the same as that graph, but we have to multiply by this extra constant, natural log of 5. The derivative, or the slope of this one, the rate of change of this one, is proportional to the original function. And that constant of proportionality is natural log of 5 for this specific example. Oops. So now we want to undo that. When I took the derivative, I had to multiply by natural log of a. And then write the original function. When I take the antiderivative, I'm doing that backwards. So instead of multiplying by natural log of a, I'm going to divide by natural log of a. So just for example, the antiderivative of 3 to the x is 3 to the x divided by natural log of 3 plus c. And if you want, you can write it as 1 over natural log of 3 times 3 to the x. Either one of those is fine. Okay, so let's look at some problems and use the rules that we've looked at so far. After we're done with some examples, we'll look at the derivative and antiderivative rules for our 6 trig functions, and then we will look at the inverse trig antiderivatives. Okay. So let's start with a simple example. Let's say you have x to the 5th plus 5x cubed minus 2x plus 3. And you want that antiderivative with respect to x. Well, I'm just going to apply all of my rules, or each of my rules one at a time. I see I've got a sum and difference here of 4 different terms. So I'm going to be using this rule repeatedly. I see a lot of powers of x, so I'm going to be using the power rule a lot. And I've got a constant here, so I'm going to use this antiderivative of a constant rule. And all of this is on your basic antidifferentiation rules sheet, the one that I posted online. Okay, so I'm taking the antiderivative of this function. How do I do it? Well, according to this rule, the power rule, I add 1 to the exponent. Oops, I wrote the derivative. That's not true. There we go. The antiderivative of x to the n. I add 1 to the exponent and divide by the new exponent. And don't forget to add that constant of integration. Now I'm going to get a constant of integration from this term, this term, this term, and this term. But one constant plus another constant plus a third constant plus a fourth constant is just going to be a 5th constant. So rather than adding 4 arbitrary constants together to get a 5th arbitrary constant, I'm just going to add a plus c at the very end. So I've got x to the 5th here, and I'm going to use this rule. So what do? We add 1 to the exponent and divide by the new exponent. And then I have a sum of several terms, so now I'm going to add. And now I've got a constant times x to some power. Here's the rule that we're using here. If you have a constant out front, pull it out. And then take the antiderivative of the function. So we bring the 5 down, and we take the antiderivative of x cubed. So we add 1 to the exponent and divide by the new exponent. Here, similarly, I bring the 2 down. There's an implied 1 there. So I add 1 to the exponent, and I divide by the new exponent. And the antiderivative of a constant with respect to x is just that constant times x, and then we add c. So this is the answer. It's just not simplified. The 2's reduce, and we end up with 1/6 x to the 6th plus 5/4 x to the 4th minus x squared plus 3x plus c. So that's it. All we did was use this rule, and I guess we used this rule as well. The antiderivative of a constant is a constant times x plus c. Now we can always check our work by taking the derivative of this, then we should get that back. I'm not going to check my work every time, but I'll just check it this time. Just so that we remember what it is we're doing. Antidifferentiation is about finding a function that you can take the derivative of to give you this function back. So if I take the derivative of this, I should get that function back. And remember what that function's called? It's called the integrand. Some really cheesy students one semester, and I say that in the most loving way. They wanted to make t-shirts that said, "You're not integrate, you're integrand." And I know that's really cheesy. And you guys are in Calculus 1, so I should tell you, this process of antidifferentiation is sometimes called integration. I'm not going to use that term until we get to definite integrals, but that's why they were making the joke. They said, "You're not integrate, you're integrand." Very, very bad joke. Okay, so you bring the 1/6 down. We're taking a derivative. And then we'll use the power rule for derivatives. So bring the power down, multiply by x to the 1 less power. So bring the power down, multiply by x to the 1 less power. Okay, then I've got a constant times x to the 4th. So I bring my constant down, and I multiply by the derivative of x to the 4th. The derivative of x to the 4th is 4x cubed. I brought my power down, multiply by x to the 1 less power. Bring the negative over. Over here, I bring my power down, multiply by x to the 1 less power. The derivative of a constant times x is just the constant. Derivative of a constant is 0. So simplify. Notice that the 6 and the 1/6 undo each other, and I get x to the 5th. So I hope you can see now how this rule will undo this rule. Because this rule says, bring the power down, multiply by x to the 1 less power. This one says, add 1 to the power, divide by that power. So we're doing that two-step process just in reverse. The first thing we did was bring the power down, then we multiplied by something to the 1 less power. To undo that, we're going to add 1 to the exponent, add 1 to the power, and then divide by the power. Dividing by that power here is the same as multiplying by that power over here, just like we see here. But the 1/6 and the 6, they reduce, the 4 and the 4 reduce, and so we get x to the 5th plus 5x cubed minus 2x plus 3. Is that our integrand? Let's look up here. It sure is. That's our integrand. So that's good. We did it right. Okay. Let's look at another one. Let's say you've got e to the x minus 2 times 3 to the x plus 5 over x dx. Now this one doesn't quite look like our rules. That one looks like one of our rules. That one looks like one of our rules. This one doesn't though. So I might want to rewrite this first by factoring out a constant. Now the constant that I see here is the constant in the numerator over the constant in the denominator. And there's no constant shown in the denominator, but there is an implied one there. So what I want to do is factor out the 5 over 1. So I'm factoring out a 5, and then I'm going to be left with 1 over x dx. And if you're not sure that that's equal, you should check it out. You want to write that 5 as 5 over 1, and then you write the 1 over x over here and multiply straight across. See that 5 times 1 over x is 5 over x? It is. That's how we multiply fractions. We just multiply straight across. So this is equal to that. And now I've got a constant times a function I know the antiderivative of. So we're going to do the same thing here that we did up there. Antidifferentiate term by term. The antiderivative of e to the x is e to the x plus c. So I see this term, I say the antiderivative of e to the x is e to the x. Here I've got a constant, I bring that down, and then I've got this function, 3 to the x. Well, that's our a to the x rule. The antiderivative of a to the x is a to the x divided by natural log of a plus c. When we take the derivative of something that looks like this, we have to multiply it by the log of the base. When we take the antiderivative, we're undoing that multiplication, so we have to divide by natural log of the base. So we'll write exactly the same exponential and divide by natural log of the base, which happens to be 3. Then I bring my 5 down. The antiderivative of x, or 1 over x, is natural log of the absolute value of x plus c, and the absolute value matters. Don't leave that off. So this is our answer. You could just put a big box around that. That would be fine. You might want to write it this way. You may not want to. It's okay. Either one is fine. So that is the antiderivative of this function. Let's check by differentiating. The derivative of this take the derivative term by term. Derivative of e to the x is e to the x. Here we've got a constant, so we bring that down. And then we multiply by the derivative of 3 to the x, excuse me. The derivative of 3 to the x is exactly the same exponential, and then we multiply by natural log of the base. And then those reduce. Then I have a 5, so I bring that down. Then I multiply by the derivative of natural log of the absolute value of x, which is 1 over x. And then I add the derivative of a constant, which is 0. So that gives me e to the x minus 2 times 3 to the x plus 5 over x. And that's my original integrand. So this is the antiderivative of this because the derivative of this gives me the original function back. Okay. Now let's look at our trig rules. Now first we're going to start with just some standard trig rules. We're going to have, I'll first state the antiderivative rules that correspond to the original 6 derivative rules. The derivative of sine of x is cosine of x. So if I'm undoing that, the antiderivative of cosine, antiderivative of this is this. So I get sine of x plus c, because the derivative of sine of x is cosine of x, derivative of c is 0. Now the derivative of cosine is negative sine of x. Don't forget your angle. Every trig function needs to have an angle. Now with the rule, we're not going to have that negative on this side, so we can multiply both sides by -1. The antiderivative of sine of x is negative cosine of x plus c. If you're not sure about that one, take the derivative of negative cosine of x. The derivative of negative cosine of x is a negative sine of x. A negative times a negative would give us a positive sine of x. And then we add the derivative of c, which is 0. The derivative of tangent of x is secant squared x. So the antiderivative of secant squared is tangent. Make sure you have the same angle. The derivative of secant is secant times tangent. Now both trig functions need their own angle. So the derivative of secant of x is secant of x tangent of x. So the antiderivative of secant x tangent x is secant of x plus c. The derivative of cosecant of x is negative cosecant of x times cotangent of x. Now, this rule doesn't start with a negative sign. So we're going to have a cosecant of x cotangent of x here. Multiply both sides of this equation by -1. So the antiderivative of cosecant cotangent is negative cosecant plus c. So we did sine, cosine, tangent, secant, cosecant, I need cotangent. The derivative of cotangent of x is negative cosecant squared x. And that corresponds to this antiderivative rule. The antiderivative of cosecant squared x is negative cotangent of x plus c. So we've got 6 new rules. All of our trig rules backwards. Notice that I don't have an antiderivative of tangent over here because there was no tangent in the derivatives list. I also don't have an antiderivative of cotangent over here. Because there's no cotangent in this derivatives list. We don't have a secant or a cosecant here because there's no secant or cosecant here. We have cosecant squared because of the cosecant squared for the derivative. We've got cosecant cotangent because of that negative cosecant cotangent for the derivative of cosecant, and so on. So these are just the derivative rules backwards. There are still 4 antiderivative rules for trig functions that are missing from this list. Antiderivative of tangent, antiderivative of cotangent, antiderivative of secant and cosecant. We will get to those later after we learn a technique called U substitution or integration by substitution. But for right now, I just want you to know your 6 derivative rules in reverse. So let's put these together. Do an example problem. So let's say you've got 2 times sine of x minus cosine of x over 3 plus 2 tangent of, or 2, not tangent of x. Let's say cosecant x cotangent of x divided by 5 minus secant squared x dx. So let's do that. Okay, now the way you want to think about this is the antiderivative of a sum or a difference is the sum or difference of the antiderivatives. So just work term by term. If I've got a constant times sine of x, I bring my constant down. The antiderivative of sine of x is negative cosine of x. Now there are 2 ways you can write this. You can either write that as 2 times negative cosine of x and then simplify in the next step. So I've got 2 times negative cosine of x, which is that. Or you can skip this step and go right here. But you can't say this but without the parentheses. A lot of students do that. You see what the problem would be if there were no parentheses here? That would say 2 minus cosine of x, and that's not what we want. What we want is 2 times negative cosine of x. So keep that in mind. I bring my 2 down, and I multiply by the antiderivative of this piece. And multiplication needs to be indicated somehow, usually with parentheses. Without the parentheses, it's subtraction, not multiplication. Okay. Now here, there is a constant multiplying my cosine of x. There is no quotient rule in reverse for antiderivatives. So I just want to pull the constant out. And the way I do that is I look at the constant in the numerator and the denominator. This is not a 3 multiplying a cosine of x. That's a 3 in the denominator, and there's an implied 1 in the numerator. I'm pulling out the negative 1 over 3, and then I multiply by the antiderivative of cosine of x. The antiderivative of cosine of x is sine of x. And there's nothing to simplify there, so I'll just bring it down. Over here, I want to pull out the constant as well. Antiderivative, or first I notice I've got a 2 in the numerator and a 5 in the denominator. So I pull out the 2/5, and then I take the antiderivative of cosecant of x times cotangent of x. If I don't remember my rules for antiderivatives yet, I can just ask myself, what did I have to take the derivative of to get this? Oh, it was negative cosecant of x. And there's your rule right there. So we have negative cosecant of x. Or we can simplify that this way. It's negative cosecant of x times 2/5. Here I bring the negative down. The antiderivative of secant squared. Say to myself, what's the function I take the derivative of to get secant squared? That's tangent. And that's our last function. So we add the c. We can check this by taking the derivative. So I have the derivative of negative 2 cosine of x minus 1/3 sine of x minus 2/5 cosecant of x minus tangent of x plus c. Bring the constant down, and I say to myself, what's the derivative of cosine? Derivative of cosine is negative sine of x. Bring the constant down. I say, what's the derivative of sine? Derivative of sine is cosine. Bring the negative 2/5 down. I say to myself, what's the derivative of cosecant of x? It's negative cosecant of x, cotangent of x. Bring the negative down. What's the derivative of tangent of x? Secant squared x. Then I say, what's the derivative of c? It's 0. So this is my answer. It's just not simplified. Negative times a negative is positive. Negative times negative is positive again. Then I look at my original integrand. Is this equivalent to this? 2 sine x, negative 1/3 cosine x. Yes, the constant's just pulled out. Got 2/5 of that. Sure, it's just a constant pulled out from that. And then the negative secant squared. So yes, it worked. The derivative of the antiderivative is the original function. Let's do one more example involving trig functions. Okay, I do the same thing here. Bring out the constants first. Look at the constant in the numerator and the denominator. There's no constant up here, it's an implied 1. So this is a negative 1/4 times the antiderivative of secant of x times tangent of x. I ask myself, what do I take the derivative of to get secant times tangent? It's secant. Over here, I pull out the constant. What's the constant? It's not a 3. It's a 1/3. So I pull out the 1/3. And I say, what's the antiderivative of cosecant squared? And it's negative cotangent of x. So I take the derivative of cotangent, and I would get negative cosecant squared plus c. Okay. So we've got our 6 derivative rules in reverse. So our 6 trig antiderivatives. I think that's going to do for right now. Later we're going to learn antiderivatives for tangent, cotangent, secant, and cosecant, and the antiderivatives that are related to inverse trig functions. I just want to show you on the sheet. I just showed you all of these. I didn't show you these last 3 yet. If you're making flashcards, you might put these on a flashcard, and we're going to go over those a little bit later. And we did talk about these first 6. These 4 we're going to talk about after we learn a technique called integration by substitution. Okay, so we've got all the rules on this sheet except for the bottom 3 here in this column and the bottom 4 here. Now, sometimes when you're faced with an integral, none of the rules work. So you look at the integrand. And you say to yourself, okay, let's take the antiderivative of this. Do I have a rule for that? I don't have a quotient rule on this list. There is no antiderivative for quotients here. So in that case, what we're always going to have to do is a little bit of algebraic manipulation so that the integrand looks like one of our rules. Actually, let me put a 3 there, just so that we can practice adjusting the constants. Now, this does not look like one of our rules, but whenever I'm dividing by a monomial, I can take each of these terms and divide by it. The reason why that works is because of this fact. Remember when you studied fractions? If you have 2 fractions with like denominators, you've got 1/3 and 4/3. So I've got 1/3 of a pi and 4/3 of a pi. How much pi do I have? I've got 5/3 of a pi. So I've got 1 pi and then 2/3 of a pi left over. The reason I can do that is because all these parts are the same size. But anyway, the idea is if the denominators are the same, these are the same size parts of a whole, I can just add the numerators together and keep the common denominator. Well, that works in reverse as well. So if I've got a fraction like this, I can say this is the same as this over 3x plus this over 3x plus that over 3x. I'm going to call this technique separating the numerator. So if your integrand looks like a rule, or does not look like one of the rules on your sheet, but you've got a fraction like this, sometimes we can separate the numerator. If the numerator has multiple terms, you can take each term and divide it by the denominator. And then after algebraic manipulation, simplifying this using exponent properties, we should have basic rules for that. So let's simplify. The exponent properties that we'll need just a few of them. If I've got x to some power over x to a different power, I subtract the exponents. Remember, if you have x to a negative power, that's 1 over x to the same power but positive, and that works in reverse. And I guess we should say, how would I adjust these rules if there was a constant in the numerator and the denominator? Well, I'd pull that constant out, just like I have been doing. And then I use the exponent property for the x to the n over x to the m. I use this one. So I subtract the exponents. Or if I have this, I can just pull out my a over b, and I'm still left with an x to the n. Or if I have this, I have a over b times x to the negative n. So we use this a lot because we're often trying to make a term in our integrand look like this. if that power is anything other than -1, I want it to look like this. Now, if that is x to the -1 power, I always have to rewrite it this way, and remember it's a log. The power rule doesn't work when n is -1, because then we would be dividing by 0, and that would be a very bad thing. The derivative of natural log of the absolute value of x is this. So the antiderivative of 1 over x, which is the same as x to the -1, is this. Again, if the exponent is -1, do this. Otherwise, it's this. Okay, so these are our exponent properties. Now, I've got all of these on your sheet. This is on the second page of your antiderivative rules with facts from algebra that you need to know. So I've got this negative exponent property, the rational exponent property, and then those three fractions that we were talking about, this one, that's another example of the same thing. Actually, I guess I have another example of that as well. But the idea is you're using all of these properties here. We're using these over and over again. I still talk about them in Calculus 2. I talk about them in Calculus 3. I talk about them in differential equations because people have still forgotten them. Once you know these, they come up all the time. It makes everything easier if you know how to simplify correctly. So when in doubt, if you're like, I don't know how to rewrite that, look at the second page of your basic antidifferentiation rules sheet. This will help you with the rewrite. Again, I see something like that, and my goal is to write it as a constant times x to the n so that I can use that rule. Or if the power is -1, I'll use that rule. Okay. So that's all on the sheet, on the second page of your sheet. So there's an implied 1 there. First thing you want to do to prepare to antidifferentiate is rewrite this so that our basic rules apply. Basic rules don't apply yet, but I can factor out the constant. That's a 1 over 3. And then I multiply by x to the right power. I'm going to subtract the exponents. X squared over x to the first is x to the 2 minus 1, or just x. The x is reduced here, so we just get a 5 over 3. Careful here, that's not 3 times 1 over x. That's a 1/3 times 1 over x. And if you don't believe me, multiply straight across and you get that. Okay, I've got a rule for that, a rule for that, and a rule for that, so I'm ready to antidifferentiate. Bring the constant down. Add 1 to the exponent and divide by the new exponent. Dividing by 2 is the same as multiplying by 1 over 2. I do that a lot, especially if there's a fraction out front. So I'm saying add 1 to the exponent, divide by the new exponent, which is the same as multiplying by 1 over the new exponent. Okay, here I've got a constant. The antiderivative of a constant is that constant times your variable of integration, which happens to be x. Bring the 1/3 down, that's a constant. Antiderivative of 1 over x is natural log of the absolute value of x plus c. Don't forget that absolute value, otherwise it's wrong. Like, what if x is negative? Then that wouldn't even be well defined. So we need to do this. That's the right answer. It's just not simplified. Multiply those two fractions straight across. And you get this. So that's one technique that we often use to write our integrand in a form that we can antidifferentiate. Now, what if you see something that looks like this? Well, that almost looks like a chain rule problem, right? But we don't have an inverse version of the chain rule, not yet. So at this point, the only thing I can do is something like this. I'm thinking of this like a binomial. It's not exactly a binomial because this isn't a polynomial, but it's the same idea. I've got one term and another term. If I want to antidifferentiate this, I can't antidifferentiate it in its current form, but if I write it twice in FOIL, then I'll probably have rules for that. So let's write this twice in FOIL. This technique I call expanding a binomial squared, or if you have a trinomial squared, you would do the same thing. So I've got 5 times the square root of x plus 1 times 5 times the square root of x plus 1 dx. Now I know I'm trying to get here. My goal is to get to a place where I can use one of my basic rules. So I need x is raised to powers. I don't want that square root of x. So I have to remember this exponent property. I'll put an m there. X to the m over n is the nth root of x to the m. The number in the denominator is the index of the radical, and the number in the numerator of that rational exponent is that exponent right here. So these guys match. That exponent is that exponent. So when I have a square root of x, it's this, but there are a couple of implied numbers there. An x by itself is just an x to the first, and a square root is an implied like second root. There's an implied 2 there. That's the index of my root. So this is actually an x to the 1/2 power. And then we just FOIL. First times first is 25. And remember this property, I've got x to some power times x to a different power. You want to add the exponents. 1/2 plus 1/2 is 1. Outer times outer is 5 times x to the 1/2. Inner times inner is another 5 times x to the 1/2. So I've got 10 of those. Last times last is 1. Now I've got a rule for that, a rule for that, and a rule for that. So I can antidifferentiate from here. The antiderivative of, well, first I'll bring my constant down, of this constant times x is that constant times the antiderivative of x. And then this requires a power rule. Here's my power rule for antiderivatives. We add 1 to the exponent and divide by the new exponent. Don't forget to add c. So I add 1 to the exponent, I divide by the new exponent. We'll have a c later after we take care of the other 2 terms. Here, I bring my constant down, then I add 1 to this exponent. 1/2 plus 1, 1/2 plus 2 halves, that's 3 halves. And then we're going to divide by 3 halves. Dividing by 3 halves is the same as multiplying by the reciprocal. So we're multiplying by 2/3. And then we take the antiderivative of 1 with respect to this variable x is just 1 times x. Don't forget your c. Multiply straight across over here. There's an implied 1 in that denominator. So you've got 25 over 2 x squared plus 20 over 3 times x to the 3 halves plus x plus c. And you're good to go there. Now, I'm not going to check this, but if I wanted to, I could. If I take the derivative of this, I'll get this. And this actually factors to that. So you should, if you're not sure about this, you should confirm for yourself that if you take the derivative of this, you get this. And then you should confirm for yourself, this also factors this way. And if this factors this way, it factors this way. Okay. So let's see, what else? What about something like this? Okay. Now think back to all of your trig rules. Do you have a rule for the antiderivative of cotangent squared x? Do we know a function that you can take the derivative of that will give you cotangent squared x back? Look at your list. These 6. Do I have a cotangent squared on here? I don't. The closest thing I have is this cosecant squared. That's what I can do here. With this one, I don't have a rule for this, but there is a trig identity that relates cotangent squared to cosecant squared, and I've got a rule for cosecant squared. The antiderivative of cosecant squared is negative cotangent of x. So if I recall that rule and I use that rule here, I can write this in a form so that my basic rules apply. That's the whole idea. I want to take the antiderivative, so I just apply these rules. It's pretty simple. If the rules don't apply, I've got to do a little bit of algebra to make it so that the rules do apply. So we're doing algebra, but it's algebra that requires trig identities in this case. So here are some facts to recall. You don't have to remember a lot of these, but you should know the 3 Pythagorean identities. They're so important. Sine squared of an angle plus cosine squared of the same angle is 1. If I take this and I divide it by cosine squared, sine squared over cosine squared is tangent squared. Cosine squared over cosine squared is 1, and 1 over cosine squared is secant squared. And if I take this and I divide by sine squared, I get sine squared over sine squared is 1. Cosine squared over sine squared is cotangent squared. And 1 over sine squared is cosecant squared. Oops, of the angle. The angles have to be the same, using A for angle. Now, I don't have an antiderivative rule for cotangent, but I know from this identity that cotangent squared of some angle is cosecant squared minus 1. And I've got a rule for cosecant squared, and I've got a rule for 1. So we can take this and rearrange it. And the reason we're doing that is because we've got a rule for that, and we don't have a rule for that. So we'll say this is the same as this, and I've got a rule for that. This one I have a rule for. This one is not quite ready for antidifferentiation. I need to rewrite that as well. This technique for rewriting is called using trig identities, which is sort of obvious, but I'm going to write it down anyway. We use trig identities and exponent properties. So I've got a rule for cosecant squared minus 1. That's just a constant times x to some power. It's a power rule. Over here, I want to factor out the constant. We've got 2 over 1 as our constant, and of course the negative out front. So that's a negative 2, and this x squared in the denominator, if I bring it up to the numerator, is x to the negative 2. And that's just because of this rule. If I've got an x squared in the denominator, that's the same as x to the same power, but negative. I often use this rule in this direction, but when I'm taking derivatives or antiderivatives, I've got that power rule, which is so powerful, right? If I have something that looks like this, I'd really like it to look like this so that I can use my power rule. Or if this x ends up being x to the negative 1, I'd actually go back and write that as 1 over x so I can use my log rule. Okay, so this is the same as this. I've got a rule for that, a rule for that, a rule for that, and a rule for that. So now I just use my rules. The antiderivative of cosecant squared is negative cotangent of x. The antiderivative of negative 1 with respect to x is minus x. Bring the 5 down. Here we add 1 to the exponent, divide by the new exponent. Bring the 2 down, add 1 to the exponent. Negative 2 plus 1 is negative 1. Divide by the new exponent. Don't forget to add your c. We get negative cotangent of x minus x plus 5 over 4 times x to the 4th. And we end up with a 2. And that x to the negative 1 will become an x in the denominator. If you're not sure about that, let's do that on the side. So this is 2 times x to the negative 1 is 1 over x to the 1st. There's an implied 1 there. We multiply straight across. So we've got that right there. Okay. That's that antiderivative. All right, now let's look at another one. If you've got, let's say, 4 over the cube root of x minus, let's say, the 4th root of x over 3 times, let's just say, 2x cubed minus 1 over the 4th root of x. Say, man, that looks hard. It's really not. It's just algebra. Do I have a rule for that? No, we don't have a rule for an antiderivative of a product. Do not take the antiderivative of this and multiply by the antiderivative of that. It does not work. You've got to make it look like the rules on your sheet. The way we make it look like the rules on our sheet is we rewrite all of those exponents. Actually, I want to mix it up a little bit. Let's make that a 3. And let's make that a 3 too. Okay. So we rewrite all of these radicals involving x as x with rational exponents. We'll FOIL, and then we should be able to use our basic rules in order to evaluate this. Excuse me. Okay, so first thing I do is I use my exponent properties again. And one of them is x to the m over n is x to the, or is the nth root of x to the m. Number in the denominator is the index of the root. So first thing I will do is I will rewrite this, rewrite each term separately. In each case, I want to factor out the constant and write this as x to some power. There's an implied 1 in the denominator here, so that's a 4 over 1. So I'm pulling out a 4. And then this is an x to the 1/3 according to this rule, but it's an x to the 1/3 in the denominator. And remember this rule? If I've got x to some power in the denominator, I can bring that up to the numerator as long as I change the sign of that power. So this is x to the 1/3 since it's in the denominator. When I bring it up to the numerator, it'll become x to the negative 1/3. Over here, there's an implied 1 here. The constant is negative 1/3, so you bring that out. And then this is x to the 4/3 power. And we've got a 2x cubed. It's already ready for antidifferentiation. There's not really a constant here. I'm just going to bring up this expression to the numerator. So that's an x to the 3/4. And I think I said this one backwards. I said 4/3. It should be 3/4 here. Sorry about that, guys. I hope that didn't lead to any confusion. If it did, I'm so sorry. It's x to this power over this power, so it's 3/4. This is also x to the 3/4, but it's in the denominator, so let's make it negative. I still do not have a rule for that because I don't have a product rule for antiderivatives. But I can FOIL, I can distribute. So the technique that we're using here is distribution. So I've got 4 times x to the negative 1/3 times 2x cubed. So multiply the coefficients, you get 8. X to the negative 1/3 times x cubed, that's x to the 3 minus 1/3, so that's 9/3 minus 1/3 is 8/3. That's first times first. Outer times outer. Multiply the coefficients first. That's 4 times a negative 1, so negative 4. And then I've got x to the negative 1/3 minus 4/3. I keep saying 4/3, it's 3/4. I'm so sorry. Okay, so we're here. I need a common denominator, so I'll multiply this by 4/4 and this one by 3/3. I end up with negative 9 minus 4, that's negative 13/12. Strange exponent, that's okay. That's first times first, outer times outer, inner times inner. Negative 1/3 times 2 is negative 2/3. Add the exponents here. 3 plus 3/4, that's 12/4, plus 3/4 is 15/4. And last times last, a negative 1/3 times a negative is a positive 1/3. And then x to this power times x to that power. If I add the exponents, that's x to the 0. But x to the 0 is 1, and any number to the 0 power other than 0 is 1. So that's gone. So I've got this, even though it looks bad, I've got rules for all of these guys. So I bring my constants down. Then we add 1 to the exponent. So I've got 8/3 plus 1. That's 8/3 plus 3/3 is 11/3. And divide by the new exponent. Dividing by this fraction is multiplying by the reciprocal. So we'll multiply by 3/11. Bring the negative 4 down. Over here, you want to add 1 to this exponent. Negative 13/12 plus 12/12 is negative 1/12. And you're going to divide by negative 1/12, which is the same as multiplying by negative 12/1. Bring the constant down. Add 1 to the exponent. So I have 15/4 plus 1, so that's 15/4 plus 4/4. So it's going to be 19/4. And we're dividing by 19/4, so that's multiplying by 4/19. Antiderivative of 1/3 is just 1/3 times your variable. Don't forget to add c. Multiply straight across. Oops, that's 24/11. 48, that's going to be an x to the 1/12 in the denominator. Oops, it's a minus. 8 over, well, 3 times 20 would be 60. It's got to be 3 less than that, so 57. Okay. So we've got that. So, ooh, that's a beast. Take the derivative of that. You're going to get that. And if you want, you can prove to yourself that this times this equals this. Or try to factor this and make it look like that. It doesn't factor very nicely. And then each of these can be rewritten that way. Okay, so let's do some more that involve trig functions. Let's say you've got secant of x plus tangent of x, quantity squared. This is a combination of those rules we've talked about. We don't have a chain rule yet. I've got a function inside another function, but I don't have a way to undo a chain rule yet. And I really don't think this is the result of some chain rule either, because there's not that extra factor, you know? You have the derivative of the outside evaluated at the inside times the derivative of the inside. I don't see any derivative of the inside. So even though it looks kind of like, well, maybe I should do the chain rule in reverse, it's not that. So I say, okay, what can I do? I'm going to combine a couple of the techniques we've already talked about. I've got a binomial or something that looks like a binomial. It has 2 terms, it's squared. So we're going to expand it. So you're going to write it twice in FOIL. Oops. First times first is secant squared. Outer times outer is secant of x times tangent of x. Inner times inner is another one of those, so we've got 2 of them now. And last times last is tangent squared. I've got a rule for that and a rule for that, but I don't have a rule for that. But I've got a Pythagorean identity. Tangent squared of an angle plus 1 is equal to secant squared of the same angle. And while I don't have a rule for tangent squared, I do have a rule for secant squared and a 1. So I can solve this for tangent squared by subtracting 1 from both sides. And then I can just make a substitution, make a replacement. This is the same as secant squared of the angle, which happens to be x, minus 1. So now this can be rewritten as secant squared plus secant squared, so that's 2 secant squared. Got a rule for that. Plus 2 secant of x tangent of x. Got a rule for that, and then a minus 1, I have a rule for that. So I can compute the antiderivative now. So bring the 2 down, and I take the antiderivative of secant squared. That's tangent. I bring the 2 down, and I take the antiderivative of secant times tangent. That's secant. Antiderivative of 1 with respect to x is x. Don't forget your plus c. If you take the derivative of this, you will get this. And you can prove to yourself using trig identities that this is equal to this. You can prove to yourself using factoring that this is equal to this. And then of course this is the same thing twice, so you know it's equal to that. Okay. Last one. Oh, whoops, just kidding. We're not ready for that yet. Getting ahead of myself. Okay, I think that's it for this video. What I highly suggest you do, if you want to learn how to take antiderivatives, you print out this rule sheet. Make sure you learn your rules. Make flashcards. On one side of the flashcard, write this. On the other side of the flashcard, write that. On the same flashcard, write an example of the application of the rule. Make flashcards for all of those that we've gone over so far, which include these 6 for trig functions, and these top ones, everything except for that bottom 3 in that first column. Make sure you know your rules, and then practice applying them. And then just remember what the concept is. Even though we're doing a lot of algebraic manipulation and it feels like, oh, you're just sort of moving symbols around. Like that's one of the beauties, or that's part of the beauty of calculus, is that we took these complicated problems, things that are seemingly very complicated. Like how do you find the instantaneous rate of change of a function at a point? And we made it into this, or we didn't make it into this, but Leibniz and Newton made it into this very simple system where, because of the limit definition of the derivative, we had these rules that just popped out. Now you know the derivative of x cubed is 3x squared, easy. Derivative of natural log of x turns out to be 1 over x, easy. Derivative of sine happens to be cosine. We have all of these rules. So we don't have to work with limits. We don't have to work with all of that stuff that we first learned at the very beginning, because all of this stems from that. And I think that that's pretty cool and very powerful. So all you have to do is learn the shortcuts, which might seem kind of tedious and might seem like memorization, but it's a very powerful tool that you'll use in this class and in Calculus 3 and in differential equations. And if you're an engineering student in engineering analysis in your third year classes at the university. So make flashcards for these, make sure you know your rules, make flashcards for these. If you want, you can start learning these rules, although we haven't derived them yet. We'll prove these later. We can prove these using the chain rule by taking the derivative of this, using the chain rule, and doing some algebraic manipulation, we can prove that we get this. But we're gonna focus on all of that later. For now, make sure you know these rules. Now at the bottom of the sheet, I gave you some common techniques for algebraic manipulation. Today we talked about expanding binomials or trinomials squared. We talked about separating the numerator. There's multiple terms in the numerator and just one term in the denominator. You might separate the numerator and evaluate 2 or more integrals depending on how many terms you had in the numerator. We'll do this in Calculus 2. We'll do this in Calculus 2. We'll do that in Calculus 2. We did number 6. So we looked at number 1, number 2, and number 6. And that's it for right now. But these are the techniques that are coming in the next course. Our goal is to use algebra and our basic rules to enable us to find the original function. If we know its derivative, we might want to get the function back. Makes perfect sense. So antidifferentiation will allow us to find that function. Also, if you need algebra review, it's on the second page of your sheet. All of these beautiful rules that may seem simple, but they're critically important when it comes to actually getting the right answer. This is what we tend to use here in this class because we like to write things as a constant times x to some power so that we can use our power rule. And some of this down here we don't see very often in this course, but you're going to see it a lot in Calculus 2. When we look at sequences and series, you see expressions like this a lot. This actually could have been an integrand. And once we know how to handle that constant times x, we'll be able to anti-differentiate that. So that's coming later. And of course, taking something like that and foiling, that could have been our integrand as well.